New topic this morning, a topic that some of you may well or not have met before, complex numbers. So it's the second learning outcome that is tested by the first exam paper. Ready? So this week, new topic, complex numbers. We're going to represent complex numbers in polar form and in what's called Cartesian or rectangular form. We're going to look at addition and subtraction of Cartesian complex numbers, multiplication and division of those Cartesian numbers, use of calculator to convert between polar and Cartesian forms, and addition and subtraction of polar complex numbers. Okay, so quite a lot. See how we get on. The other thing I'm going to be doing is looking at where we are. We missed a week, and that's pretty tight. So we might have to start half an hour earlier for a week or three to catch up. Alright? But the last thing I want to do is not have enough time at the end, 2 weeks at the end, to revise the two papers. Okay? So, use of complex numbers in is it brief exercise? What do you get if you become Yes, sort of. It's a little bit more error. There is no real solution to square root of a negative number. Real solution. Because the math square root of a negative number. Complex number. This complex solution of a negative number, but not a real solution. Not who has covered this topic? I know these two have last year with me. Check. Remember doing maybe a long. Right. So represent. We can do it in two forms: Cartesian form. So the Cartesian axes axis and the vertical axis is called or vertical component. So real component, vertical component. Okay, and then we have polar representation. A number is represented by 3. The angle 30 degrees, say. Or it could be in 45. Be 3 angle minus 40. It's 3 angle 315 degrees. Positive angles go that way. We're using as a note, if these are amps, say that is as 3 amps angle minus 45. And the okay. Over here, we've represented on this scale what the mathematicians have done, and the mathematicians use the letter I, because I is used in engineering so extensively for current, engineers use J. Okay, so depending on whether you look at a maths textbook or whether you look at an engineering textbook, Bird's is an engineering maths textbook, so he uses J, by the way. But this is the positive real axis, so a positive real number. J represents this axis. Remember, J, or you should know that J is equal to the square root of minus 1. Okay. Now, as we go round here, this point is equal to J squared. What could I also write that as? Remembering J is equal to the square root of minus 1. What happens if I square that number? It becomes minus 1. So this axis over here is actually minus 1. I put the J squared in a circle. Yep. Just move that down a bit. This here is J to the power of 3. What could I also write that at? Remembering we said that J squared is minus 1. Yeah. J squared equals minus 1. 2, we've got to square that. It's minus 1 times J. We've got to multiply that by J, so the result is minus J at the bottom. See that? J squared is minus 1. So J cubed is J squared. Let's write it like this. J cubed is equal to J squared times J. So if j squared is minus 1, that's minus 1 times j equals minus j. So down here is equal to j cubed, or you can write it as minus j. So on the vector on this Cartesian representation, we represent it as 4 steps plus 4 steps on the x-axis plus 3 steps on the 4 plus 3j. If we're in, so that's in the first quadrant, we've got a positive real part and a positive. In the second quadrant, minus 4 on the real axis, because we're left, and then we're going positive 3 upwards, minus 4 plus 3j. So we get a third quadrant, they're both, because we've got minus 4 on the x-axis, minus y-axis. And then in the last quadrant, in the fourth quadrant, we get an imaginary part. It's always worth thinking about what, if you're talking about an angle, if I'm knowing that if I'm over 90 degrees but less than 180, I'm in the quadrant, and I should, in my calculations, end up with a negative real part, and the other way round, knowing that that 4 plus minus 4 plus is going to be an angle with 980 degrees. You can, it's worthwhile to answer look right. Yeah. Okay. So these two number types, we've got, for example, 4 plus 3j. Just to start, x-axis, imaginary part. Y-axis. This time, 3 angle 30 degrees. The mathematicians call, but we're engineers. I'm going to magnitude. 3 amps. Mathematicians call that angle, e.g. direction. Okay. These numbers, using those type of numbers makes sense. High form, you how many volt courses you want to end up with your answer, engineering wise, in this volts to represents direction it's in terms of angle. This tells you nothing about that vector in units. Alright, if that was representing the current, you'd just say it was 4 plus 3j, and mean it's 4 amps and it doesn't mean it's 3 amps. You'd have to convert that to this form and show you how to use it. Although I don't know about Nat with his chart, but I expect that'll do it. We'll see if we can, okay? But how to convert with calculations between the two types. Alright? So, at how we do calculations of complex numbers. We're going to start off with the Cartesian or J type numbers, how we add them together. Or addition, two complex numbers are added or subtracted by adding or subtracting separately the two real parts. So, for example, if we've got a vector quantity z, graphically, yeah, possible if vectors are drawn carefully to scale. Here's 4a on 3 on the x-axis, 4 down the y, drawn a vector. Here's 2 plus 3j, 2 plus 3j, the resultant vector is that one in there, x-axis, x1, sketch as well, show you whether you're in the right, sure whether you've got it right. A quick sketch will show you whether you're in the right area. Okay, when we talk about subtraction, got 2 plus 3j, 3 minus 4j, with minus 3 minus 4j, and then the parallelogram comes up here. We end up with just wanted to show you that it is possible to do it graphically, and a quick sketch sometimes checking whether your answer's right on a ballpark. Right, problem. Given z is equal to z2 is equal to 3 minus j, determine z1 plus z2, z1 minus z2, and z2 and we'll go through them. Right, what we got for now? What do I write? Yeah, that's the right answer. So I'm going to put on here where that come from. So that's 2 plus 3 plus 4 minus 1j. Yeah, so that is 5 plus 3j. So just start with. Haven't got anything different. That comes from 2 what? How easy it is, but wrong. So what does that bit equal? 4j minus j. Be careful. I'll show one way around that problem in blue, and that's definitely around that problem. Certainly in electrical stuff, we may well be adding 4 or 5 voltages together. Kirchhoff's law problem towards the end of slightly differently. 2 minus 3, 2 plus 4j, sorry. Underneath, write 3 minus j, the subtraction that way. 2 minus 3, 1. It's 4 minus j, j. And I like that method. You're doing subtraction, so that's plus 4j minus j. So the two negatives make a plus, don't they? All right. Personally, I think writing them out like that equals less mistakes. So applying that method to this one, 3 minus j, take away 2 plus 4j. 3 minus 2 is 1, minus j, minus 4j, minus 5j. Is that what you got? How? So you went 3 minus 2. 2 is 1. Minus minus 5j. Well, operation is subtraction, not addition. Yeah. Right, and it serves to be a warning that you need to be careful with your signs in all of this. Yeah. Yeah. I personally, I would do it that way. Yeah. I am. I'm trying to be persuasive. Use this method because the other way is fraught with danger. Yeah. Okay. Multiplication. Multiplication of Cartesian complex numbers. This is achieved by multiplying out the brackets and using the fact that, as we've already said, Cartesian Roem. Go on to that, let's find it. What was it? That. We said that j squared equal to that's a key part to both multiplication and division. Cartesian number is equal to 1. See in a minute. So we've got two numbers there. J applied by a problem like this, possibly you use an Ohm's law or do a parallel impedance in electrical circuits, AC circuits, because you're using product of a sum. So you get two impedances. Right? Just trying to put it in context. So let's have a look. I'm looking for this. Right. What we do, multiply out the brackets. So what's the method for multiplication? Well, if we're multiplying two bracketed terms together, so I'm just going to write it out a bit bigger 3 plus 2j times 4 minus 5j. 3 times 4, 3 times 5j, and then we multiply. So 3 times 4, 12. 3 times minus 5 minus 15j. 2j times 4 is minus 5j. Minus 10 j squared. Hang on, so now we'll simplify. 12, no other. 15j plus 8j minus 7j, and this 10 times j squared, and what's j squared equal to? What does that make that? $12 minus 7j plus 10. So the simplification is minus 1, so it gets rid of that term a constant, changes its sign. Yeah. So if this on the end here was positive, and so of Cartesian complex numbers. All right. So have a go at those ones.